Hello. Today we're going to talk about um, entropy and the second law of thermodynamics. So first, entropy. So entropy symbol is used as S, and S, we define the change of entropy. Okay. So there's a delta there. It's equal to the heat that's required, and then divide by the temperature. Okay. And this temperature has to be in degree K, Kelvin, and that's in joule. Okay. All right, so we're going to give an example to demonstrate this. So the example that we have is we have M1 equal to 50 kilogram. And T1 is 20 degrees C. And then there's another bucket of water. And M2 is also equal to 50 kilogram. And T2 is equal to 24 degrees C. Okay, so we're going to mix them together like in a bigger container. So now, as you can tell, this is 50, that's 50. So the temperature final is going to be a T prime, right? It's going to be equal to 22 degrees C. And this total M is going to be equal to, T prime is equal to 100 kilogram. So in this process, the M1 is changing, and M2 is also changing, right? So let's calculate the Q, right? So the Q, right? So they'll calculate calculate the entropy change for the one, right? So it's going to call that delta S1. It's equal to Q1 divided by T1. Okay, so we have 20 degrees C. Okay, and then become 22 degrees C, right? So for this to happen, right? So that's equal to Q1. So what's Q1? Q1 is equal to MC, so M1 C, and then delta T, right? And this delta T here is equal to M1 C, and delta T is equal to 22 minus 20, right? So final, subtract the initial. Okay, and this C is for the water at 20. That's roughly 4186 and joule per kilogram per, in this case, degree C. It's okay, right? And so M1 here is 50. Okay, so then you can see 50 times 2 is 100. So it's going to be 4.2 times 10 to the 5 joule. Okay, so that's for this side here. How about for this side here? So it's dropped the temperature, right? So delta S2, it's equal to Q2 divided by T2, okay? So we're going to put this one back there, okay? And what's Q2? So Q2 is equal to M2, 50 kilogram, times C times delta T, okay? And this is equal to 50 times 4186. So we're going to assume the 4186, the specific heat doesn't change that much. So delta T here is 22 minus 24, right? So it reduced the temperature. So that's minus 2 there. Okay? So that's Q2 is going to be equal to 4.2 times 10 to the 5 also. But there's a minus sign there. Okay? So that's Q2. All right. So now we're ready. We're going to switch color here. We'll change color. We're ready to compute the delta S1 here. So this is equal to 4.2 times 10 to the 5 divided by T1. So this T1, it's this 20 degree there. So just 20, but we need to use degree K for this computation, plus 273. Okay? So that's 293, and then 4.2 times 10 to the 5. Okay? So we're not going to work it out, but you can do that yourself. So Q2 is 4.2 times 10 to the 5, but has a minus sign. And then T2 is this one here, 24. So it's going to be 297, right? So you can see this is the same value on the numerator. The denominator, this one's bigger, right? So this one here, when we add the delta S1 and delta S2 together, so they mix. So this delta S1 is happening during this process. In this process, delta S2 is happening. So together, when you mix this 2 buckets of water together, the total delta S is equal to delta S1 plus delta S2. You can see this one is smaller denominator. So this one is more positive than this one here. Okay, so this is smaller value. So together, it's going to be larger than 0. All right, so what we demonstrate is the second law of thermodynamics. Okay, so in a natural process, when we mix this 2 buckets of water together, the entropy is increasing. And that statement, it's called the second law of thermodynamics. So that's one of the statements, okay? So the second law of thermodynamics says the following. Says that in the natural process, in this case, it's a mixing 2 buckets of water, right? The total entropy increase. Okay? So the total entropy of any system plus that of its environment increase as a result of any natural process. All right? So this is one of the statements of second law of thermodynamics. So we're going to stop there, okay, until next time. All right? Hopefully you have a little